Okay, in the last class we discussed about nuclear fusion, uh, which is happening in Sun and other stars. Today we will start a new module. This is the particle physics. Before we go into that particle physics, before we discuss about the particles, let's consider the four fundamental forces in nature. So, four fundamental forces. So this include gravitational force, electromagnetic force, strong force, and weak force. So first we consider gravitational force. So as we know, this gravitational force is responsible for majority of macroscopic behavior when you consider the solar system, galaxies, Earth geometry, its shape, as well as the sun geometry. All those heavenly bodies are strictly controlled by this gravitational force. So this is nothing but which this force is responsible for. Responsible for most macroscopic behavior. Let's consider some examples as let's say solar system, galaxies, and its geometry. And sun its geometry, that's shape, etc. So all these heavenly bodies, their motions, their different orbits, all those things are controlled by this gravitational force. Uh, Also, if you consider any heavy body interaction in Earth's surface also, it is also having an effect because of this gravitational force. So this gravitational force will be having some impact if the body is having some mass, considerable amount of mass. If the mass is very small, then the force will be weak. So if you consider that properties, then this force is always attractive in nature. It's always attractive in nature. Then it is having infinite range. It means that it will be influenced even if that the bodies are very far away. So it's a very long range force, but it is weak. So if you consider two masses, let's say and which are separated by distance r, then by F, we can have this gravitational force F, which is proportional to m1 product of those masses, by closely proportional to this power of distance. So by using this equation, we can explain many things happening in the macroscopic world, but there are some exceptional cases, like Curie orbit. So this was the equations or the idea put forward by Newton. But later, Einstein explained this gravitational force as curvature in space and time. So by Einstein, the gravitational force is nothing but you can say that disturbance in space-time continuum. Disturbance time. So if you consider that special theory of relativity, we have that fabric of space and time. Suppose if you consider time like this and space like this, that is x, y, z. This one line and t another line. So if you put any mass to this space-time fabric like this, then this space-time fabric will be having some curvature or it will be having some disturbance. So we will just go like this. So we have some so it will make that space-time continuum or space-time fabric that will be having some kind of perturbation or disturbance because of this mass. So this makes suppose I will put it again here. Suppose this is initial space-time fabric that will become almost like this. It will be like this. When you put some mass, it will become like this. So if anything which is coming to this range of that gravitational force or this curvature in space, that will be attracted towards this. So this was the idea put forward by Einstein through special theory of relativity. But even if you are having that Newton's law of gravitational force, it itself will have beautiful explanation. It will explain all the heavenly body expressions. And by using this expression only, we are still sending rockets to the space. We have different satellites, all those things, all those are working with this expression F equal. So this is still valid. Yeah, this is some other view of the same force when you consider that special theory of relativity, and you have space-time fabric. This is your space-time fabric. This is, suppose this is your space as capital X. So it includes X, Y, Z, and then we have time which is in this axis. So if you are having mass, then your space and time will be having some deviation from its origin. Okay, so this is about the gravitational force. So I will just put some properties here. Otherwise, I will put that at the end, compare all the forces. Now the second one is electromagnetic force. When you consider this electromagnetic force, if you consider any atoms, molecules, all those things are formed by using this electro force. So this electromagnetic force exists between any charged particles. Okay. So the force, this force exists in any charged particles. We can say that atoms uh, okay, so if you consider atoms, inside the atom there is nucleus and the electrons are revolving around this nucleus. Okay, so it is basically positive charge at the center and the negative charge electrons are revolving around that. So the attractive force between these two, that is in between that nucleus and electrons, or for atoms, the attraction between those nucleus and electrons, that is because of this electromagnetic, that is through this electromagnetic force. And if you consider any nucleus. Inside the nucleus also there is proton proton, there is some repulsion, proton proton repulsion in nucleus. It is also because of this electromagnetic force. We consider that any molecules which are also formed by using this electromagnetic, all kind of molecules and these are formed with like any molecules, any molecule consider that will be having this electromagnetic force which will be binding them. So in all these we can observe this electromagnetic force, and if you consider the basic properties, then particles with the uh, magnetic or electric properties, they will show this. And this will give you that properties like hardness, softness, elasticity, all those things will be determined by this electromagnetic force for a given material. Also, these solids, liquids, gases, all those states, it's also determined by this electromagnetic. So, how much there is attraction, how much there is repulsion. With respect to that, the state of the matter will. So we can say that this will be this electromagnetic in some or most of the case, hardness, softness, we can say elasticity, etc. Such properties. Similarly, we can say that this voice also leads to the different states like solids, liquids, gas states, determining these states, solids, liquids, gas states, which also depends on this electromagnetic force. Then if you consider that electromagnetic waves, EM waves, it is again responsible, this force is again responsible for that electromagnetic waves by this duplicate, have that whole spectrum from sunlight or the things which are nothing but electromagnetic waves. So these electromagnetic waves are from force or indirect. And we have all those Maxwell equations, everything, all Maxwell equations which are also related with this electromagnetic force. We have different E, cross E equals 0, del dot E equals E. So all these equations which we derive from for that electric or magnetic fields. And the modern theory for this electromagnetic force, apart from that Maxwell equation, modern theory for this explaining this electromagnetic force, which is nothing but that quantum electrodynamics. So according to this quantum electrodynamics, when the particle interacts, they exchange photons. When the particle interacts, they exchange photons. So this electromagnetic force, the force carriers are photons. Force carriers are photons. So when two particles, charged particles or magnetic particles, which when they interact each other, okay, so when they interact, they will exchange photons between them. This exchange of these photons is responsible for this electromagnetic force. So when they exchange these photons, there will be attraction or repulsion depending on that nature of particles. Okay, that is from this quantum electrodynamics. And if you consider here, if you are having two masses, M1 and 2 as I said here, so there will be some exchange of particle also here. And these particles are nothing but gravitons. They are not yet discovered, but this is some kind of a theoretical approach. When the gravitation force is associated with the exchange of particles, which are called as and in the case of electromagnetic force, we have the photons as force carriers, which will be exchanged. Now we'll discuss something about the next one, which is the strong nuclear force. Strong nuclear force, or we can say that it is strong force. So in the case of strong force, we already discussed many properties of this when we studied the nuclear physics, nuclear structure of the things. So all those properties will come here. These are charge independent force, spin dependent force, then you have that short range force. All those what we discussed earlier, these are short range force. So short range means uh, if you take that potential diagram, and it will be like the potential diagram will be like this. So this is your potential curve with R. So if you go beyond some distance, let's say some few femtometer or some like nuclear range, it depends on that size of your nucleus. So some few femtometers range, you can observe that force. But if you consider that when your particles are very close to each other, let's say this is some 0.8 femtometer. So if you go less than this zero point 0.8 femtometer, your separation between those nuclear particles less than 0.8. Then the potential become positive, which means that the force will become repulsive. So in this region, the nuclear force is repulsive. In this region, it is attractive. In this region, it is zero. Nuclear force is zero. So only some very short range it is having that. If it is in between 0.8 centimeters and 2 centimeters, and it is going to be attractive force. And if it is going beyond this 2 centimeters, then it's a short range force. It is having both attraction and repulsion nature, depending on the separation of those nuclear particles. Okay. So how these nuclear force are happening, that we'll discuss more in detail next section. But let's say that some points here about this nuclear force. So strong interaction happens between quarks through gluons. Okay. Strong, just understand this. Strong interactions happens between quarks. We will discuss about these quarks and all this later. So strong interaction happens between quarks through gluons. Gluons are the particles. So we'll discuss about it later. Okay. And residual strong interaction which happens between the hadrons, between hadrons between hadrons through ions. You can say ionisms or ions. We'll discuss what are these ions later. So this is a basic idea behind this nuclear force. So if you consider it, it can be also called as nuclear force, strong nuclear force. Then it is having different names like strong interaction. You can call this as strong interaction. Nuclear force is strong interaction. Otherwise, you can also call it as color force. Because this quarks having, we represent them with different colors. So that's why it's called as color force. We'll discuss about those things. So if you consider the nuclear force, as we discussed, it is short range, spin dependent, very strong force, perceive when particles are very close to each other, attractive and between 0.8 to 2 centimeter, and repulsive when they go very large distance. You can say very larger than 2 centimeter. So as the distance increases, then it will. Okay. And if you consider the strong interaction between those quarks, we'll discuss about the quarks later. That is through gluons. These gluons, in between those quarks, nuclear force is the strong nuclear force. And that nuclear force between those quarks are through these gluons, the interaction of this, exchange of these gluons. But when you consider that the interaction between those hadrons like proton and neutrons, interaction between those proton and neutron, in that case it is through pions. So which means that if you have proton and neutron, here there will be exchanging ions in between them as they are force carriers. Okay. So that will be through pions in between those hadrons. So we'll discuss about those class of particles, classes. So since we have quarks, these quarks with the different colors, we also call this process color force, and it is also called as strong interaction. So these are all about this strong force. So it is short range, very attractive. And now the fourth one is weak force. Fourth one is weak force. And this is not that much weak, but compared to strong force, it is weak. So this weak force, when you consider different, for example, beta decay process, beta decay process happens if you consider that negative beta decay process. For example, C614 decay, nitrogen 7 plus 1 electron plus 19. So in this case, we are having this beta decay process, and this in this process, one neutron is converting into a proton plus an electron plus and an electron neutrino. And these neutrons are made up of one up quark and two down quark. This will become one two up quark because proton is having two up quarks plus that electron plus mu. So we'll discuss about this quark structure and all those things later. So just understand that this neutron having three quarks with the up, down, down. This proton is having three quarks with the up, up, down. So this from this one D is converted into U. One down quark is converted to one upper quark and become it will become proton plus electron. So this is the basic beta negative beta decay process. But in this process also, in this beta decay process, if you consider this particular process with the Feynman diagram, then you have UDD, which is converted into UUD. This you convert into U, this D converted into U, this D converted into U, sorry, D. So when this happens, there is an exchange of W boson. This, and then you have those, you know, and electron. So this will happen that D converts into U, this D converting to U, all other things are same, this U is same, but this D down quark is converted into up quark here. So in this process, one omega bosons come from this reaction, and that immediately decay into one electron antineutrino and one. This is what is happening. So this interaction is nothing but a weak interaction, or we can call it as a weak force, which will be happening in this kind of interactions, beta decay process. process. Okay, so these interactions, which will uh, this is explained by electro theory. The theory associated with weak force is electroweak theory. And these kind of weak interactions are necessary for the radioactive decay processes. So these kind of interactions are necessary for different radioactive processes. And these are also uh, necessary for buildup of heavier elements, the weak forces are also necessary, because when you consider that fusion reaction and all those things, we can observe these beta decay actions. So if two lighter nuclei combine together and form heavier nuclei, we need this kind of interaction. So these are also necessary for uh, necessary for build up. You can say necessary to build up the heavier elements. And we also know that this kind of interaction violates the parity. Okay, so that's all about the four fundamental forces, or four fundamental interactions. Some descriptions I have given here. You can look for more explanation regarding this. Now let's just compare these four interactions. So if you consider those theory first, so the gravitational force, if you consider theory, so the gravitational force is explained by general theory of relativity. General theory of relativity. And in the case of electromagnetic force, it is quantum electrodynamics. This is called the QED, general theory. Then the strong nuclear force is explained by quantum thermodynamics. Is QCD. Then we have this last one, that weak force, which is explained by electro weak. So those are the theory associated with these four fundamental forces. And if you consider range of these forces, range will be infinity for gravitational force, infinite for the electromagnetic force. Even though it is infinite, it will be weak. It's also very weak. And then we have the strong force. Strong force is very short range. Okay, so this is short range. Short range which is in the order of 10 to minus 15 meter. conformity, we can say. And then we have 10 raised to minus 18. This is weak fraction, so 10 raised to minus 18. Now, if you consider relative strength. So in relative strength, I will take gravitational force as 1. So with respect to gravitational force, this value 1, how much will be the other force? That is the relative strength. So if I take gravitational force as 1, then the electromagnetic force will be 10 raised to 38 times of that gravitational force. So 10 raised to 36 here. 10 raised to 36, that is for electromagnetic force. This will be 10 raised to 38 times of that gravitational force, and this will be 10 to the power 25 times. So this is weaker compared to the strength as well. When you consider the relative strength, this is weaker. That's why it is called as weak force. This is weaker than the strong force and this electromagnetic. But it is still larger than gravitational force. Now, if you consider the force carriers, here we have that gravitons. They are not yet discovered. And then here we have photons. And in strong force, we have two different types, so gluons and pions. So gluons for the interaction between quarks, interaction quarks. So in those cases, we have exchange particle as gluons, and interaction between hadrons, that will be through pions. And the last one is weak theory, or we can say weak force. So weak force will be through different bosons, W plus minus Z bosons. So these are some comparison of these four forces. You can add more to this list. These are the important factors. By comparing, we have to compare the theory associated with it, the range of those forces, and their strength, and the force carriers. You can add more properties to this. So that's all about this four fundamental forces. But I have explained some of their properties, how they exist in the nature, what are their importance, all those things. Then we discussed about comparison. We compared their strength, their range, areas. Okay. So that's all about the four fundamental forces. Now we will discuss the Yokawa theory of nuclear force, meson. So let's consider Yokawa. So I will just go through this theory and check it in different references for further understanding. So Yokawa's meson theory. So we discussed about the strong nuclear force that is between those nucleons inside nucleus. So if a neutron which is interacting with a proton, through this strong force, strong nuclear force. So there will that this interaction will be through ions. So exchange of some particles could happen in between these nucleons, neutron, proton. So this was first predicted by Yokawa by saying that there should be some particles which are exchanging this in between this neutron and proton. So when they exchange some particles between them, then they feel it as some kind of attractive force, attraction, which exists between them. Okay? So the Yokawa's meson theory predicts that the nuclear force exists because of exchange of particles. Okay? So the neutrons and protons are continuously emitting uh, neutrons and protons continuously continuously emits and absorb uh, these particles, and these particles are mesons. The particles called mesons. So this is the basic of this Yokawa meson theory. Okay. So which means that if you have a proton that will become neutron by exchanging one pi plus. This is pi meson, pi plus meson. So pi plus plus one neutron, and a neutron plus pi plus, that will give you this proton, which just release one pi plus and becomes neutron. This pi plus will be absorbed by the neutron, and so this will happen within a very short range of time, and this will happen continuously, the exchange of ions in between this neutron and proton, and that result in some kind of attractive force in between proton. So how this is coming? If you consider proton-proton interaction itself, you have two protons. Your electromagnetic force cannot explain how these two protons can be attracted inside the nucleus because they are same kind of charges. They should repel each other. But according to this Yokawa theory, if they are exchanging some particles continuously within them, then there exists some kind of attractive force in between them, and that attractive force leads to the strong nuclear force. So even though there is a Coulombic repulsive force through that electromagnetic interaction, but since there is interaction of or exchange of these particles, ions in between them, they will form some kind of effect. So these pions, because of this exchange, these protons cannot come very close to each other because when they are carrying And also, if they are very far away, they cannot exchange these particles. So in order to exchange these particles, mesons, they should have some particular distance. They should keep some particular distance, and they should not go away from that particular main distance. Close, very, they will not come very close either. So that's why we are having that potential is attractive when they come very close to each other. So consider this point if there are that suppression is less than this 0.8 femtometer. They are not able to exchange these pions because we are very close to each other. So if you consider that badminton play, if those players are very close to each other, they cannot play. They are very far away also, they will not be able to play because they cannot reach that much of distance. Same scenario will happen here. If they are very close to each other, they cannot exchange these pions or mesons. If they are very far away also, they cannot exchange those pions, so they will be having some. So when they are very close to each other, they will try to repel each other. When they are very far away, their force will become zero. And in between them, we have some range of r or distance, where we have that attractive force between the proton and neutron. So it is charge independent. So this is the Yokawa theory, some theory for this nuclear force. And if you consider this particular action, this is a proton which is converting to pion plus neutron. So how this mass conserved in this particular equation, because if you consider proton which is decaying to neutron, but we have one additional particle pi plus pions, so this mass will not be conserved here. So if you consider this proton and neutron mass, we have additional mass pi plus, so this is not conserved, mass is not conserved. Then we have to consider that Heisenberg uncertainty principle with that energy uncertainty. Okay, so if you consider del E dot del T, this should be greater than or equal to h cross pi. Okay, so if you consider that interaction, if this interaction is having some length L, these are the two particles which are having this particle that pion exchanging between them. These pions exchanging this. So if they are separated by a distance L, let's say, and the pi mesons will be having some velocity. They are exchanging in between these neutrons with the velocity, let's say, which is almost equal to c. So the time while this exchange happening, okay, that time, that will be equal to L is L length by c. So this is the time by which this exchange is happening between these two neutrons. These pions are exchanging within that time. Okay, this time, now, if you consider that this equation and substitute this time interval here, and also we have energy which is equal to mc square and pi c square. So m pi is the mass of pion. Now, if you substitute all those values here, then we'll get m pi c square times L by c. For calculation, I will take this approximately equal to h cross. Now, one c will get cancelled here. And if you take that L length as 1.7. Assume this L is 1.7 or 2 femtometer we can take. Then let's say that m pi. So this will give you m pi times c times L, suppose 1.7 centimeter. We take this c into other side 1.7 centimeter to other side on, and h we know that Planck's constant. So then you will get m pi, which is equal to 220 times mass of electron. So experimentally, it is observed that this m pi is having experimentally it is observed that there are some particles which is having some mass of which is in this range, which was observed around 273. Another particle with similar mass, which is call it as 150, which is nothing but 264. So around this range it is coming. So which means that experimentally we observed these particles with mass of 273, 264. Which means that this particle exists, and from where these particles comes, according to that, if you consider that Yokawa's theory, then they will be coming from that from nuclear. So these are the particles which are responsible for those nuclear. So experimentally, it is verified that these particles are there, are existing. So probably the Meson theory forward by these Spanish scientist Yokawa, that also will be right. Okay? So these particles later these particles were experimentally observed. So this is all about the Yokawa theory of strong nuclear force, or Yokawa Meson theory. So basically, this predicts that there is an exchange of particles between those nucleons, apart from those Coulombic interactions. So this exchange of particles results in a strong interaction between those nucleons. These particles are nothing but ions or pi mesons. And when we calculate their mass, theoretically, it is coming around 20 mass of electron. And experimentally, it is found that there are some particles which are having these masses of this range, and probably that will be the pi meson. So experimentally, later it is verified these particles exist. So the nuclear force, the interaction between those nucleons happens through this particle exchange as predicted by Yokawa. Okay, so that's about Yokawa. Now we'll discuss about some other topic. If you consider these are the particles, is there any other particles exist in nature? That the hunt for other particles also started here. Then we have different varieties of particles, and there are some other set of particles which having some properties different from their counterpart, which are called as antiparticles. So these antiparticles are having some different nature from their counterparticles. So if you consider an electron, the antiparticle of this electron is positron plus. So they are having some different in their charges or other properties remain same. So if you have any particle, if two particles interact each other and results in complete annihilation, then such particles are particles and so if two particles when they interact, that will give you complete annihilation. Annihilation means they will disappear, their mass will go, and complete energy will be given. If two particles interact and completely annihilate, then that those two particles will be, one particle will be particle, and the other one of that set will be particle, and the counter one will be its antiparticle. Okay, let's say electron, this electron interacting with one positron plus, then this will produce radiation that is nothing but gamma photons. So when you consider these two, you have the electron thrust mass energy, which is for electron, which is MEc square, which is nothing but 0.511 mega electron volt. Same for the case of positron. So total energy when they annihilate, that will be nothing but 2 times 0.511 mega electron volt. Okay. So basically, we have two photons which are coming out from this process, two gamma photons. So these photons will be moving in different directions. This will be in the opposite direction to conserve those uh, momentum. They will be going in the opposite direction. So this gamma will be having 0.511. This also having 0.511. So we will be having two photons, two gamma. So they will be, in order to have that momentum conservation, so they will be moving in the opposite direction with the energy 0.5. So this particle, when they interact with, when it interact with this, its counterparticle, which is the antiparticle of that electron, that is nothing but proton. That complete annihilation happens in this interaction, and that will produce pure energy. There is no mass, and that energy will be coming out from this interaction as photons with energy of 0.511 photons. Okay, so then we call these two are particle and antiparticles when they annihilate completely. Okay, now if you consider proton, you have antiproton. If you consider P as your proton, the antiproton is P bar. Another case, you can consider any other uh, particles, any other neutron or any other particle. So if you consider that electron will be having anti-electron. So when these two neutrinos, this electron neutrino and anti-electron neutrino combine together, then you will get a pure energy. So that will produce pure energy. If this proton and then this proton and this antiproton interacts each other, then it also produce energy in the form of photons. So all those mass will become energy. Then this proton and this proton bar, which are particle energy. So when an antiparticle interacts with particle, it will they will completely annihilate and produce pure energy. So that's about the antiparticle. I have given this antiparticle discussion because we will be using those antiparticles in the upcoming discussions. So I have given some introduction to that. What are exactly these antiparticles, so that you will understand it much more clearly. Now we'll discuss about the classification of particles. So there are different kinds of particles. So according to their nature, we have to classify them. I will be discussing about those classification of particles, and then we'll go to the properties, different observations of those particles. So those things we will discuss after that. So first we will consider the classification of particles. So you can make it as particle or matter. Discuss about classification of particles. So classification of particles, we can take this as particles of matter. So this first one is leptons. So leptons are the particles, they do not feel the strong force, do not feel strong force. So these are the particles that do not feel any strong force. There is no strong interaction happens between leptons. And second one is that they are subject to the weak force. Are subject to weak force. Okay. So the leptons interact each other through weak force. So they do not interact through strong force. That is what this means. They do not feel strong force. They are subject to weak. And these are fundamental particles. That is, that cannot be split up into anything else. Okay. So these are fundamental particles. So fundamental particle means they cannot be divided further. Split into anything else. So these are fundamental particles. No, they cannot be split up. So suppose if you consider atoms include electrons and protons, neutrons in nucleus. So the atoms can be further divided. They can be split up into the particles again. Okay, but if you consider these leptons, they cannot be split. They are the fundamental particles. There is no particles which can form those fundamental. So this set includes electron. This set includes electrons for these particles. These are the particles. Electron, muon, electrons, then muon, and prons. So, so these are the three different particles that we can have. Tron or particle. So this is represented by. Okay. Then we have here for electron we have positron or those antiparticles. So before that I will write electron neutrino here. Electron this electron neutrino that I will represent by E. Then we have neon neutrino. This mu. Then proton is neutron. And antiparticles. So this means that for electron we have positron. For muon we have the antiparticle of this muon. So this is this. Then we have and you have that electron. This neutrinos also having that antiparticle bar and bar. So you just check this. Uh, so this bar representing that it is antiparticle. If there is no bar, then it is antiparticle. So that's about leptons. These leptons are not subject to the strong force. They are not interacting through strong force. They are interacting through weak force, and they are fundamental particles. They cannot be divided into any subatomic particles, subparticles than this. So electron, muon, proton, they cannot be divided further. Okay, so these are the set of particles which comes in the electron family. And now we will go to this second class. This is the exchange particles. So these are the exchange particles. So exchange particles. So exchange particles are nothing but they transmit 4 forces so we discussed already about this. When the interaction happens through those 4 fundamental forces, there will be exchange of particles. Those particles are called as exchange particles, and they transmit 4 forces of matter. Now, this include as we discussed electromagnetic. In the case of electromagnetic, we have photons. The photons are the exchange particles, and in the case of gravitational force, gravity, we have gravitons. And in the case of strong force. So in strong force, we have 2 different exchange particles, as we discussed. So in strong force, we have gluons. These gluons are the particles which we use, which will be interacting or exchanging between those quarks. And we can also have those pi mesons in between those proton and neutron inside. These 2 are possible for strong. And the last one is weak interaction. So in weak force, we have those W or Z bosons. So this is W plus or minus, and V plus or minus. Plus or minus or bosons. So those are the exchange particles. Now we'll discuss the next class. The next class is nothing but the hadrons. So hadrons are these are made up of quarks. These are made up of quarks, okay, and they feel strong force. Now, if you consider in this case of hadrons, we discussed about quarks. So quarks are different types. So we call it as quarks with up, down, and charm. Down, strange. Then we have a top, bottom, top is top, bottom, and then the last one is so up means U, down means D, strange means S, top is T, bottom T, charms. So these are the 6 quarks And by using these six quarks, we have the hadrons are made. Okay? So they are made up of these quarks. These quarks. And these quarks are fundamental particles. Fundamental particles like leptons. These quarks also fundamental particles, which means that they cannot be divided into some other particles. So the hadrons are made up of these quarks, which are fundamental particles, and they feel very strong force. Okay. So in these hadrons, we have two classes. We just put here. So we have two classes here for hadrons. So they are mesons and baryons. Okay. In case of mesons, they are made up of quark-antiquark pairs, made up of quark antiquark pairs. So antiquark means we discussed about quarks. Similarly, there will be antiquark. For example, antiquark for up is U bar, antiquark for down is D bar, antiquark for strange is S bar. Similarly, here T bar, B bar, C bar. These are the antiquarks corresponding to those six quarks. Okay, so then mesons will be having one quark and its antiquark or any other antiquarks. So quark antiquark pair. So basically, it is quark antiquark pairs. They are made up of quark antiquark pairs. Okay, mesons are made up of quark antiquark pairs. Okay. Then, for example, in this case, we have three different particles. One is pi mesons. We already discussed about that. Pi mesons. And pi mesons, we have pi plus, pi 0, and pi minus. Then we have k mesons. Okay. In k meson, we have k plus and k 0. And then we have eta. Also here. And they are antiparticles. Pi meson, we call it this as pions. We also call this as kaons. K-A-O-N, kaon. This pi mesons, this set and their antiparticles. I will give another chart include all those particles. Here only I am just classifying. So this set pi, pions, kaons, and eta with their antiparticles. Then baryons, in case of baryons, these are made up of three quarks. Three quarks. We can say that they are consisting of three quarks. So those three, here we have two quarks, one quark and anti-quark pair. Here we have three quarks. The baryons are made up of three quarks, which can be anti-quark or quark, depends on that. So they will be having three quarks basically. So in this case, we have again classification here, these baryons. These baryons are classified into two further. This nucleon, nucleons, and then hyperons. And these nucleons, they are nothing but protons, neutrons, and they are antiparticle. In hyperons, we have a set of particles. Say that the first one is delta plus plus the minus. Then we have sigma minus sigma plus. We have cascade plus cascade 0. Then finally we have omega of lambda here. Not like that. So that also comes in this class. Because we are in that order 4, 3, 2, 1. Then also we have that lambda. So all these particle and their antiparticles. And particles. So these are the classification. This is the classification of particles. Basically, we can classify like this. So there are leptons, exchange particles, hadrons. So if you exclude this exchange particle, then it's leptons and hadrons. And leptons do not feel strong force. They are subject to weak force. They are fundamental particles. They cannot be divided into further. They consist of electron muon and electron and they are antiparticles. Which is nothing but the particles which act the particles, other particles. They are the force carriers for forces, forces. And if you consider electromagnetic force and these photons, gravity, which is electrons, strong force, gluons, and mesons. Then weak force, we have W, and bosons. Okay. Then hadrons. And the third classification, which is hadrons. Hadrons are the made up of quarks. They are made up of quarks. Then they feel strong force. They are responsible for strong force. And this strong force, they are not responsible, but they are interacting by one another through this strong force. And these hadrons are further classified into mesons and baryons. Mesons are made up of quark antiquark pairs. So two quarks, two particles. Okay. So quark antiquark pairs. They consist of pions, pi mesons or pions, kaons. We have it. Also, we have baryons. Baryons are made up of three quarks. Okay, so they consist of three, three quarks. They are made up of, and it is kind of classified again. Baryons are classified into nucleon, hyperons. And in nucleon, we have proton and neutron. They are antiparticles. And hyperons, which consists of all these particles. So we discuss about further details, yes, more details about these particles and their interactions in the classes. And I will give you one more chart which will just include all these particles, only those particles, and then its classifications. So to understand the class of